Hi everyone, welcome to my presentation. I will talk to you about C++ in deeply embedded systems, modern code on tiny chips. Deeply embedded systems are mostly written in C instead of C++, even today. What are the possible reasons for that? Well, first of all, there might be no compiler, no certified C++ compiler available for the chip of choice. Also, there is insufficient or missing C++ expertise of a lot of embedded software developers. And there is a dissemination of half-truths and myths. For example, that in comparison to C, C++ has an inherent overhead in terms of performance or code size, or that C++ is a bad choice for other reasons. I'll give you one example. This is an email by Linus Torvalds a few years back. I'll give you a few seconds to read it yourself. It's worth it. So this is one of many examples where misinformation and personal reservations about C++ are spread. Also, developers can be quite religious about their choice of programming languages. So in this talk, I try to demystify a few of those myths of C versus C++. My presentation has one main part. In this part, I answer 3 questions you might have for your deeply embedded system that you're maybe gonna develop or already have. Can you actually use C++? Why should you use C++? And how much of C++ can you use? After that main part, I will also, from my own experience, give you 2 recipes. One for transitioning a code base from C to C++, and one for transitioning a team from C to C++. So let's get started. First, a bit of context. From whom and for whom is this presentation? Imagine you're in the following situation. You would like to transition your deeply embedded C code base to C++. But the code base is fully operational and it will stay like that for the next few years. So it means you cannot accept even a single day of your code base not being operational and working. So we had the same, exactly this situation in our team about 3 years ago. A bit more background on that one. So the company I'm talking about is called Sonova. Our headquarters are in Switzerland, and worldwide we have about 14,000 employees. Our main products are hearing aids and cochlear implants. The team I'm talking about is a team of about 20 embedded software developers. My position in that team is the role of the software architect and also developer. The code base I'm talking about is an embedded controller firmware running in the hearing aid and the cochlear implant. And it's not a signal processing part that's on a separate chip and separate code base. Here I'm basically talking about all the rest apart from signal processing that it's running actually on the hearing aid. This software is developed according to IEC 62304 standard for medical software. The approximate size today is about 150 lines of code spread over about 500 modules. And the whole thing runs on a small embedded real-time operating system. Deeply embedded for us means we have our custom ASIC. It's like a sub-millimeter chip that is in the hearing aid, needs to be very small. And yeah. And this one is based on an ARM Cortex M0, runs about 5 megahertz and has 128 kilobytes of ROM and 144 kilobytes of RAM. So that's the system we are working with. And over the last 3 years, we have made the following achievement. We have successfully transitioned our entire code base from C to C++14. And the code base was operational the entire time. So we have in that time released dozens of products from the code base. And it was there was not even a single day where it was not operational. So for you, if you have got this question, for your deeply embedded system, can you use C++? First, my answer is the following. You might initially run into the following problem, which is the first one a lot of people run into. The choice of chip might be already set in stone for a particular product or project. And the available compilers do not adequately support C++. Short term, there's not a lot you can do, but in a lot of companies, long term, it's possible even for like software developers to influence the choice of chip. And maybe you can influence for the next product, the next project, you can have an influence. And for that one, I suggest you choose a chip with a large customer base that increases the availability of C++ compilers considerably. As an example, I chose the more or less obvious one, ARM. For ARM, there is this ARM compiler 5, also called Kyle sometimes. This has been out for quite a long time. It's optimized for C, so it optimizes C code really well. You get very small executable code with that. Unfortunately, as soon as you do C++ with it, the optimizations become a lot worse. It also only supports C++11, and that's not even fully. So they have noticed that as well, and since a few years, there's this new ARM compiler 6 out. This one is not based on ARM compiler 5 anymore. It's based on Clang. So they more or less completely rewrote it. This one supports, fully supports C++14. And it's also expected to support later revisions in the future. It also comes with the usual Clang features, like, for example, link time optimization. So for an ARM-based, as a summary, an ARM-based chip with ARM compiler 6 is a good choice for your C++ deeply embedded system. Now, why should you use C++? So this is a C++ conference, so maybe you don't need a lot of convincing, but bear in mind that you might be in the future in a position where you need to convince someone else. So keep listening. First of all, what you probably would like to do with C++ is object-oriented programming, OOP. And there is a strong desire to use OOP out there, even with C developers. Maybe you have seen that as well, that a lot of C code bases, people actually try to mimic OOP concepts. For example, have a look at this. We have a struct here, which is called myClass, which would be a class. There are some member variables here. And there are operations on that class, like an init and a foo operation. The class or the struct gets allocated, initialized, and used. And if you look at that closely, it's actually nothing else than what you see on the right-hand side. It's just the mimicked approach of a class with member functions and member variables. This was also in our code base. When it was C, you could see this one a lot. So if you do it the proper way with C++, what you get is better syntax. So the syntax is easier to read, shorter, and therefore less error prone. Also, you can have public and private declarations. Here you can have them in comments if you like, but they're not checked by the compiler. Here they're checked by the compiler. Also, you can have proper constructors and destructors. Here, these init functions, you might forget to call it. And normally this results in a quite hard to debug bug because stuff is then not initialized correctly. And if it's on the stack, it's even worse. It's initialized differently every time. Here, it's no way you can forget the constructor. The compiler will do it for you. So you might say, okay, this doesn't look too bad. It's still quite maintainable. Well, maybe yes, but if you also try this, you also want to try this mimicked approach for virtual functions, and I think you really don't want to try that. So what other reasons are there to use C++? First of all, macros are not necessary anymore. If I program in C, in a lot of cases, I am forced to use macros. For example, for constants, in most cases, I just need to use macros. Also, if I want to have something calculated at compile time, I need to use a macro. A very simple example here, I just want to initialize a variable x with some pre-calculated value. Unfortunately, I make a mistake and I have chosen a char here, which is too small to hold the number. So what happens? Compiles fine. The result here will be x minus 122 instead of the expected 134. The program will run, and somewhere way down here, something will misbehave. I will spend quite a bit of time for debugging, and I will find the bug. Okay, let's try to do that in C++ without macros. For a constant, I can use the const expr, which is typed. Instead of the macro function, I use a template function. The usage looks pretty much the same here. And unfortunately, I make the same mistake here. But now the compiler makes a slap on my hand because, and I can see it's actually a compile error, and I notice it immediately. Why? Because macros there's no type information here. And here there's this t. It's instantiated with a char. And, well, it realizes that 129 doesn't fit into a char. So I've saved myself quite a lot of debugging time here already. The other advantages of not using macros are increased type safety, again, and also better syntax. For example, those safety parentheses that we need with macros, they're not required here. In general, this results in fewer bugs and fewer hard-to-debug bugs because a lot of stuff can be detected at compile time. In general, with regard to compile time calculations, you can use basically two mechanisms. One is the compile time evaluation of const expr expressions that has been there since C++ 11, and with every C++ revision, it becomes more and more powerful. So you can do that for functions and operators. Now, also, what has been there for a long time or since ever is template metaprogramming. With that, you can also do a lot of calculations at compile time. But there's a warning. In general, with templates, you can do like a lot of cool stuff and cool optimizations with templates, but you have to be careful. If you don't know what you're doing, you might blow up your code, so your code size might increase dramatically if you're doing the wrong thing. So if in doubt, always check what the compiler does. Regularly check the compiled code. Okay, one of those cool optimizations you can do is the following one, just as an inspiration. This is a simplified example of our handmade exception handling. We have here this throw exception function that just takes an exception type, a code, as an argument. Now, everywhere in the code, when an exception could happen, for example, in every assert, that's hundreds or even thousands of places in the code, we have to call this function. And now what we did, we introduced this wrapper template function. It just wraps the original function, takes the exception type as a template argument, and converts it to a function argument. Now you might think, well, what's the point of that? The compiler will just inline it, and then it's the same again, right? No, the compiler is smart. It will not inline it. It will do the following. Look at the assembly output here. The compiler actually instantiates those functions. Here you see one example for the exception type number 6. It will create this function. It will load this number 6 in R0 and then call the original function. And in those hundreds and thousands of places in the code, it will just call this function, which is just a branch linked to that function. Now, what's the point? Why is that good? So this move here, if it's not here, if we call directly, this move instruction would have to be here hundreds and thousands of times. But now it's here, and if you have like a handful, like 12 or so, a dozen of those codes, we have maybe about 20 or so. It's only here 20 times instead of 1,000 times. So every time you save those 2 bytes of this instruction, and in our code base, we were able to save kilobytes of code just by that optimization. You could now say, well, I can do that in C as well. But for that, you would need to implement everything by hand. So for every possible exception key enumerator and for every use of it, you would need to hand code one of those functions here. And whenever the use changes or you add or remove something from this enum, you would have to modify this handwritten code. This sounds like quite a code maintainability nightmare. So I would never do that in C. One last cool thing you can do with C++. Assume you have a system like that. It consists of a bit of ROM, a bit of RAM, and NVM. It is set up such that when you switch it on, it's booted from ROM. There's a bootloader that loads code and data from NVM into RAM. And then it will run the whole application as a mix of RAM and ROM code. So there will be function calls back and forth between ROM and RAM. That's actually how our system is set up. NVM changes or can change often. There can be firmware updates. That's not a problem. ROM will change every few years or so. Now, you have a mylib class in ROM. It just calculates something, and internally it uses several functions. For example, this function foo here. It is used by my user class in RAM. And now you discover a bug in this function, in this foo function, which is in ROM. And your ROM has been taped out already. It's maybe already installed in your customer's devices out there in the field. Now you want to fix this bug. What you could do is you could just re-implement the entire class in RAM, so you can distribute the bug fix via your firmware update mechanism via NVM. That might be not an option because there could be dependencies between ROM classes. Also, you might be short of RAM and you just cannot afford implementing all those classes in RAM when you want to fix just a single bug or a single line of code here. So what you do, watch here, before you tape out the ROM, you put a virtual here. And then what you can do later on, you can just derive a class, mylib class patched, and override this single function that is buggy. And as you all know, you should never write large functions. So normally that's quite a small function and you do not spend a lot of RAM to fix this bug. Now what's left, you just have to use this new class instead of the old one in your myUser class. And yeah, you have perfectly fixed your bug without consuming a lot of RAM. Okay, so let's go to the next question. How much of C++ can I use? So deeply embedded means normally that just few hardware resources are available. For example, CPU cycles or RAM. So in this talk, I give you an analysis of overhead in compiled code, depending on the various C++ language features you might want to use. All the numbers I present are based on the following assumptions. namely that you use the ARM compiler 6 toolchain and the compile target is ARM Cortex M0. However, I do not expect the numbers to change a lot just when you take another compiler or another ARM 32-bit target architecture. What I also assume is that exception handling is disabled, and so is RTTI. So the results. So please ask questions at the end, but I'll still reply to that question now. So the question was, why do I assume that exceptions are disabled, but I've just brought an example of exception handling. So yes, we have disabled exceptions here, and initially I said that's a small example of our handmade exception handling. So the point is in handmade. So because we have disabled exceptions here, we had to create a handmade one. It's basically just one function. If it is called, the system is shut down. So in the hearing aid, it's a safety shutdown. You switch off everything so that you cannot harm the patient by, for example, producing a noise that's too loud. So it's just a safety shutdown. And exception handling means you can throw an exception, but it will always immediately end up in a safety shutdown. So no throwing, catching, or whatever. Okay, so here are the results. The first results. The following simple but still very useful C++ features have zero overhead. So, for example, namespaces, const export, static assert, enum class, and also default function arguments and overloaded functions and operators. So let's continue. Object-oriented programming. For simple OOP language features, for example, with simple, I mean it's just classes, which includes private public declarations, constructors, destructors, and simple non-virtual inheritance. For those simple OOP language features, what do you think is the overhead compiled to mimic the implementation? I'll answer that for you. The overhead is 0. Okay, and you see on the right-hand side just a simple example of that. Now, look here. I now insert a virtual here, and this brings me to advanced OOP language features, which now includes virtual functions, virtual inheritance, etc. Here, in this case, the compiler has to generate so-called vtables, which produces overhead. So, and these are the numbers. So for every virtual class, there's one vtable, and the initial vtable size is 16 bytes. Then for every function you define as virtual, there's 4 bytes added to the function jump table in that vtable. And then, in addition, if you call such a function via base class, there's an additional 2-byte overhead per call. And finally, for every class instance, there is a 4-byte overhead for the pointer to the vtable. So that's it. Yes, it's an overhead. It's not too much, but still there is overhead. However, a mimicked approach in C would probably have a very similar overhead. Okay, let's move ahead. The standard template library. And here's, like, first time in this talk, bad news. Most containers in the STL are not suitable for deeply embedded systems. That's our experience. And the main reason for that is that STL containers have hidden dynamic allocation of heap memory when you add container elements to containers. In a lot of embedded systems or deeply embedded systems, you just don't want to have that. Also, what we observed, especially with ARM compiler 5, means exception code that is present in the STL is not optimized away and blows up the code quite considerably. Fortunately, there is one welcome exception, in the STL the unique pointer. This has no overhead at all, and I'm very glad about that. So alternatives, what could you do? What's the alternative for not using or for not being able to use STL containers? Well, you could just not use containers at all, and you could just implement the data structures by hand. That sounds a bit painful at first sight, but actually for deeply embedded systems, it's quite a viable option. You will see later why. What you can also do is you can use intrusive containers from Boost. Those containers, for those containers, the metadata is part of the container element type. So it also means that adding an element to a container is a by reference operation, in contrast to STL where it's a by value operation. The advantage here is that there is no dynamic allocation involved when you add a container element to a container. The drawback, obviously, there's also a drawback. One element can only be added to a predefined set of containers, which is mostly just one container. But I would say 99% of use cases, that's okay. The overhead here we measured is, again, none compared to an equivalent C implementation. However, we did not test all the intrusive containers. We just tested the most important ones. What you could also do is just a combination of the two. You could implement your own container library. So we did it for the following two containers. We invented a fixed size map tailored to our needs. This is just implemented internally with an array and linear search. Sounds horrible, the first sight, but actually it's exactly what we want because we know number of elements is small and more or less predictable. And also we have to save every byte of code, of instruction code possible. And also performance is not too much of a concern in our system. So this implementation, very simple, is really exactly what we need. In the C versions before, it was just implemented over and over again in about 20 places or 30. And now we have one place with the implementation. Same thing for a max size vector, which is internally just an array and the length information. Okay, so let's go to the second part of my talk. How to transition a code base from C to C++. I'll present you a recipe in 4 steps. The first step is let the compiler interpret your C sources as C++. As you all know, C is almost a subset of C++. There are only very few exceptions, and they are quite well and concisely documented in this Wikipedia page. So what you could do is, what you should do is you just configure your build system to tell the compiler to do that. So normally it's just changing a command line option, or in some compilers, you just have to change your file name from C to CPP, and that's it. You will stumble over a few problems, I guess. So maybe you're not in the exact C++ subset. You have to do a few modifications. You will see everything here, what you need to do. Maybe you have some problems with linker symbols, but they're all, from our experience, quite small and easily solvable. And a fun fact that for us, this change, so from C to CPP, did not change the compiled code at all in 99.9% of cases. I can only remember one case where it actually changed the compiled code. The important thing here is for this step that you do the entire step at once, like you do it first, and you do it for all the modules in your code base at once. Otherwise, if you don't do it like this, you will run into problems. For example, you will have problems with name mangling because C modules have no name mangling, C++ modules have. If the linker tries to put them together, yeah, this causes problems. Also, you might have modules in C and C++, and you have a module in C that depends on one in C++. You include the header file, and it's not in the C subset anymore. all those kinds of things. They're all solvable, but it becomes very messy very quickly. Also, if you do it all at once, there's a cleanly defined point in time where the code base and the team basically leave the C subset. Okay, let's go to step 2. And in this step, you modify the code to use simple C++ language features. The goal here is that the entire code base already profits from better syntax and readability and increased type safety. The modifications I suggest here are, first of all, use namespaces instead of prefixed module names. If you have large C code bases, very often you have a naming conventions that all the symbols are prefixed with the module name, which makes a lot of sense to avoid name clashes. In C++, you can just use namespaces, and everything is a lot simpler and a lot more readable and maintainable. Also, I suggest you use the following C++ features like the C++ bool, in case you have your homemade bool in C, which we had. Also use static assert whenever possible, const expr instead of macros, and template functions instead of function macros. Also, I suggest you use scoped enums instead of C-style enums. However, here I have to make one exception, which is especially true in low-level systems or driver code. If you use enumerator values for arithmetic operations or bit fiddling, I suggest you do not use scoped enums. They are type safe, and they are too type safe for that. You will end up with casts all over the place. So after this step, the advantages you get better syntax and readability and increased type safety. And also an observation we made in our code, even after all those modifications here, most of the compiled code was still exactly the same byte for byte. The third step, in this step, you convert all the obvious mimicked OOP code from C to C++. You might remember this example from the beginning. This is basically what you do in this step. The advantages you get here, again, better syntax, readability, and increased type safety. And I could actually make a template just for this expression here. It comes over and over again in this talk. And you cannot forget calls to something like init or destroy. They're just always made by the compiler at the right places. Also, you can have a clear declaration of what's public and private, and it's also checked by the compiler. Okay, so the last step, use advanced OOP features and further C++ language features. There's a warning, so this last step should be taken with care. I would first evaluate which C++ language features shall be used in your code and how exactly. So for example, you could say, we do not use the STL. Or you could say, we do not use virtual functions, which is probably too strict for most systems. But you never know, if you have a deeply embedded system, even that might make sense. Then you should write down your findings and decisions in authoritative coding guidelines for your team. And this is also very important. Do not try to take this last step comprehensively for the entire code base. The last 3 steps, you can do that, but not for this step, because the effort is way too high. You should only take this step for modules that you create from scratch, that you write new, and for modules that have to undergo refactorings anyway. That's at least the way we did it. And our experience with that, yes, you will end up in a mix of C-like old code and new modern C++ code. In our experience, this actually works quite well. And your entire code base will continuously change its style over the months and over the years from C to C++. Okay, let's you don't only have a code base, right? You also have a team, and you have developers working on that code base. And very often, this aspect is neglected. And I want to explicitly also have a look into that and give you a recipe here as well. So imagine you have to follow, you are in the following situation. You would like to transition your code base, your deeply embedded code base from C to C++, and you have a team of experienced C developers. Okay, what can you do? Well, we had the same situation in our team about 3 years ago. So here's what we did. It worked quite well. So that's a recipe for you if you want to follow it in 4 steps. The first step, we organized an internal training, C++ training. We hired an external C++ lecturer. He came to our office for 1 full week. We split our team into 3 groups. First beginners, second intermediate C++ users, and then last the advanced group. The training was tailored to those groups and also to the team and to the environment as such. So there was less talking about STL, for example, and more about memory management. The timing is also important. You should try to organize the training more or less at the same time when you actually start actively using C++. Second, we involved the advanced group in coaching, especially code reviews, but also presentations for the rest of the team. Third step, new hires. We started focusing more on C++. So in job descriptions, we started focusing more on C++ than on embedded, which attracts more people that come from the C world, from the C++ world compared to C. And the goal here is to infuse this team with the C background, to infuse it with more C++ mindset, which is should be as free from C-isms as possible. Fourth step, coding guidelines. I already mentioned them. It's important to have them, and you also need to continuously adapt them to the team's growing C++ knowledge over time. So the conclusion, yes, there is a powerful subset of C++ that is suitable for deeply embedded systems. It allows a developer to write safer and more maintainable code than in C, and it also allows them to implement optimizations that would not be possible in C. Unnecessary overheads in compiled code can be avoided by strictly staying in the aforementioned subset, and also by reviewing and modifying this subset. You do this by evaluating the compiler's output from time to time and for specific language features. Our first 4-step recipe allows you to transition a code base, a deeply embedded code base from C to C++ over a flexible period of time while staying operational the entire time. And our second 4-step recipe allows you to do the same for your team. So I'm ready to take questions now.